Okay, welcome everyone. It's good to see everyone joining us today for this special session of Virtual Science Camp where we're joined by Kelly Foyle, who's a physicist from the Perimeter Institute in Canada. You guys will notice I'm wearing a Canada t-shirt because I'm originally from Canada, even though I've been in France the past decade and a half. And it's really great to be joined for her. Perimeter is one of the most advanced theoretical physics research institutes in the world. And they have amazing teacher programs and outreach programs, including some new online stuff. Like they've had online stuff before, but I've really learned a lot that I've been able to model some of the stuff they've done with me for these camps. So part of my techniques comes from learning from other great people like this. So it's really an honor and a pleasure to get to welcome Kelly here to do this activity on exoplanets. So thank you again for joining us today.
Thanks, Michael. I'm excited to be here too. I see some people already have their equipment out and ready, so I'm very excited to get started. I'm going to share my screen with you now because I have a presentation. Sometimes in Zoom, you'll notice that the panel of pictures of participants might be over top of the slides. If that's the case for you, you can go to the top menu bar and you can select side-by-side view so that you can see the people on the side and the screen on the other. Just a little bit about myself. Feel free to put in the chat to introduce yourself as I'm introducing myself. My background is in astrophysics, so I have a doctorate in astrophysics, but I work at the Perimeter Institute now in education and outreach. So that means I get to share all kinds of fun science with students and teachers and with the general public. And at the end of today's session, I'll try to share with you some other things that you might be interested in that we have online. So as Michael mentioned, the Perimeter Institute is a physics institute. We study all kinds of cool stuff here, from how did the universe begin, what are black holes, how do they form, what's in the inside of them. We study things like what are in the very heart of the smallest subatomic particles, what's inside an atom. It's a really cool place to work, and there's lots of really cool things going on there. And so today we're going to talk a little bit about exoplanets, which is also a topic that is really exciting in physics now. The first thing we might ask is, what is an exoplanet? So in our solar system, we have 8 planets. Pluto was demoted, but around other stars, we expect that there's other planets as well. And when a planet is orbiting another star other than our sun, we call that planet an exoplanet because it's exterior to our solar system. And for a long time, scientists thought it would be very hard, if not impossible, to be able to detect exoplanets. And to give you a sense of why that might be the case, I wanted to share this picture of the sun. And if you look very closely, you should be able to see the planet Mercury transiting in front of the sun. It's the little dark dot just off center here. And so this is a picture that was taken. Mercury transited in front of the sun in November. And this just gives you a sense of how tiny, this is in our own solar system, how small this planet is relative to the sun. And it gives you a sense of how difficult it might be to detect a planet going around a very distant star, right? So the star is going to be so much brighter than the planet, so much bigger, it's going to be very difficult for us to be able to see an exoplanet. But things have come a long way. This is a exoplanet tracker that's on NASA. So you can go to this website, and every 3 or 4 days, they update this list. You can see here that so far we have over 4,000 confirmed exoplanets. So that means we've seen these planets go around their parent star at least 3 times. There's another 5,000 exoplanets that are waiting in the hopper. That means we think there's exoplanets around those stars, but we have to confirm them. And of the ones that are confirmed, 3,000 are in planetary systems. That means there's more than one planet. So this has come a long way, and in a very short amount of time. In 2019, Mayer and Kellos, who are on the right, won the Nobel Prize in physics for the discovery of the first exoplanet orbiting a sun-like star, and that happened in 1995. It's a while ago, but that was the very first, and now we're into 4,000. So it's really a field that is exploding. There's lots of exciting science going on, and that's kind of what I wanted to share with you today, is one of the most popular methods of finding exoplanets. And that method is called the transit method. And so this is a little animation that shows here a distant star, and in front of it, the planet is passing. At the bottom underneath, you're going to see a graph, and the graph is showing the brightness of the star, so the light that we get from the star, and then you're going to see the planet pass in front. And what you'll notice is that the brightness dips down. So the planet is blocking some of the light from the star. So each time the planet goes by, it blocks some of the light. And that's how the transit method is used to detect exoplanets. Astronomers point their telescopes up to a distant star, and they watch it for many, many days, sometimes years, and they watch to see if there's a little dip in brightness. And that dip in brightness tells us that an exoplanet could be there. So we're going to simulate this today. We're going to do a simulation. Some of you, I see Eloise here has her planets ready to go. We're going to try to simulate this today and see if we can use our cell phones to detect the exoplanets that hopefully you guys made with your cardboard circles and your sticks. So what we're going to do, you might have a flashlight like this. You might have a desk lamp. You might have a lamp where you've taken the shade off. And you should ideally have two exoplanets, a big one and a small one. The other thing we're going to use is a smartphone app. So on your phone, you should be able to open up, if you have an Android phone, you can use the physics toolbox. When you tap on the menu bar, you can choose a light meter in your app. Okay, that's going to be what you'll use. If you have an iPhone, you can use Science Journal. So both of those are free and available for you to download. And in both cases, we're looking for a light meter app, something that's going to measure light and also plot a graph. Okay, so I'm just going to briefly switch. I'm going to stop sharing my screen for a second so that I can switch and show you the setup that I'm going to use. So I have a stack of books so that I can prop my cell phone up. Depending on what camera the app is going to use, you're going to want to make sure the camera of your phone is directed towards your light source. Like I said, you could use
and Kelly, just to interrupt for a sec,
yeah.
You're a little bit less loud than before. Is it possible to speak louder or to move your microphone a bit closer?
Absolutely. Just 1 second.
And also just to relay a question that came up in the chat, there was something about the star itself can be brighter or less bright, which I think came up when you were showing the animation with the transit method, with the dip and the graph at the same time.
For sure. So the stars can change in brightness for a variety of reasons. Particularly as a star enters the later stages of its life, it will go through all kinds of changes in brightness. But the signature that a planet leaves is very different from those types of signatures. It's as we'll see when we do the experiment, it's going to be a very narrow dip. And there's ways that we can model what a planet might do in terms of blocking starlight, which is going to be a very, very tiny blocking of light, versus something that might be happening in the outer layers of the atmosphere of the star, and what those things might look like. So we can model those different phenomenon, also using our own sun as a guide, and get a sense of what are the chances that something like this could be produced by a planet versus produced by a star. Is the volume okay now, Michael?
For me, it sounds great. Yeah, if anyone's having any problems with volume, let us know so we can change it. But I think that fixed things perfectly. Thanks, Kelly.
Okay, great. So what we can do is we can set our cell phone up with the screen open so that you can see the graph of your light meter. You're going to have your camera pointed towards the light source. Depending on the app you have, you might need to select the camera that you're going to use, either the one that's the selfie camera or the one that's that points outward. So depending on your setup, you may need to adjust that. On the Physics Toolbox app, it'll show a luminescence on the vertical axis, and then it'll show time on the x-axis. So luminescence just means brightness. And then I'm going to use a desk lamp. Again, any large light source. So you wouldn't want to use a cell phone flashlight here, but a big flashlight like this would work, a desk lamp, a lamp without the shade on it, any of those things. But you might need to adjust the height of your light source or the height of your phone so that the camera is in line with the light source. So that could mean that you need to put your phone up on a stack of books. So especially if you're using a lamp that's much taller, you'll need to get your cell phone in line with it by using a stack of books. And what we'll do is we're going to turn on the light, and then we're going to simulate the passage of an exoplanet using the cardboard cutout circles. Now that's what the setup is, but before we actually do the experiment, I'm going to come back over here, and we're just going to talk a little bit about what we might predict. So in science, it's always a good idea to first ask yourself, what do you think is going to happen before you go ahead and make any observations? And so we're just going to, you might have that handout. If you don't have it, that's not a big deal. It's a pretty basic handout. You might have that handout, and on the first page of the handout, it's going to ask you to make a prediction. The first prediction is, what is that light curve going to look like if a big planet, a big exoplanet, went in front of the star? How would that curve look in comparison to one that was a small planet? So how does that light curve change or look different based on a big planet going by versus a small planet? Part B of the prediction page, so that same first page, asks you to compare the speed of the planet. So whether it's moving slowly or fast as it transits in front of the planet. Are there any questions about what we're making the predictions for?
And just to help some of the people, because we intentionally left a fairly wide recommendation for age. So for some of the younger ones, you might be a little bit less used to graphs like this. So the brightness, when the planet's not passing in front, it should be at 100% at the top. So that's what you should expect. And if there's no planet, it would just be 100 the whole time. So you're looking at how the amount it would lower would change depending on a planet in front of it. And that, the first part, big planet versus small planet. And the second, the planet going fast versus slow, the same size between the two second graphs.
Yeah, that's exactly right. So if you think it's a good idea, Michael, we could go into breakout rooms and people could chat together about what they think.
Yeah, let's give that a try. So I'll divide into breakout rooms. About how many do we want in each breakout room?
think 4 is good. 4 or 5. Probably 4.
Perfect. Yeah. So if we have 5 breakout rooms, it'll be 4 to 5 people per breakout room. And I'm just going to remind or request to everyone, if it's possible, to have your camera and your microphone on so you can more actively discuss with other people. It's good to do that in the breakout room. I know that some people, they either don't have the strength of an internet connection or might not have a camera that's equipped to work with Zoom. So in that case, don't worry if there's anyone in your room that appears to be silent. They're probably not just intentionally ignoring you, it's because of technical reasons. So bear that in mind, but if you can turn those things on, please do so in the breakout room. So you'll get a link to join the breakout room. Please join that, then you'll have a couple of minutes in that breakout room to discuss your predictions with each other. And I accidentally ended the breakout rooms a little bit early when I was trying to enter someone from the waiting room.
I had a good chat with Eloise and Vernita and Susan in breakout room 1, and it seemed like they were kind of on track. So I think we can probably carry on.
Excellent. Yeah. Did we want to go to the poll, or were we?
I think let's switch over to the activity now. The poll is a bit wordy, so let's just see if we can give it a try. The setup, everyone together. How does that sound?
Yeah, that sounds great.
Okay, so ideally, if you're following along, you should have made your predictions on page 1 of the handout. Now we're going to do our observations. Now, sadly, I can't share the screen here of this phone in the way that I would like to, but what you're going to do is you're going to try to do each of these planets at least 3 times so that you can get a sense of the curve. I'm going to switch cameras again because I also want to mention something else that's pretty important about your setup.
And one thing, just to jump in on the setup too, I'd meant to mention earlier, but you had mentioned people need to check if it's their front or back camera. Like usually by default, it'll be by the front. But just one way to quickly check that, although there's a lot of glare on my phone right now, is if you cover your camera with your finger, then the intensity should drop all the way to 0. And that's a good way of seeing it's that camera rather than like my back camera. I cover that and that didn't affect the graph at all. So if there was any questions still on which camera you were using, that's a really quick way you can test that.
That's a great point. And you should probably do a couple of tests just at the beginning to get a good sense. The other thing is that sometimes if you've played with the display on the phone, you may have zoomed in. So if you can look at your vertical axis, you find you're not really seeing anything. Sometimes it's because you zoomed into a part of the graph where there's no line at all. So that can be another problem. The other thing is that unlike a real system, right, where we are very, very far away from the star, our lamp here is actually going to be quite close to our phone. And that means that it's actually pretty important to make sure that your planet is the same distance from your fake star. What I've done here is I've put a piece of tape to be a guide marker for my eye, but any little thing that you might have, you might just make a mark or you might put something, a piece of paper down, just so that you keep the distance of the planet the same from the star the whole time. For a very distant system, this distance is so tiny that we don't need to worry as much about it. But here, this is going to play a role. So this is one way in which, you know, our model is not a perfect match to what is actually going on out there. So when you turn the light on, you can watch and hopefully see a change in your graph. As Michael said, you can test it by just putting your hand in front of the camera, putting your hand in front of the light. And then you're going to choose one of your 2 planets. The first one that we were going to do is we were going to compare big versus small. And you're going to want to take the planet and pass it in front of the star, your fake star. And you'll want to do it a few times. Now I'll just show, I'll do a couple more times and then I'll just try to show you my screen. and try to make the passages roughly the same speed. Because we want to keep all of the other variables constant, because right now we're just going to compare size. So you can see here, hopefully, maybe, I've got some nice dips that are happening in my graph as the planet goes by.
And if anyone's got some good results to show, can you hold those up to your camera too, so we can see that who's got this working for them? I did my last one while talking, so mine's not as good as Kelly's was, but I think she's had more practice too.
So I'll do a couple more here. And a few things, right? If your hand is a little bit shaky, if your arm, if you misplace your arm, you might block some of the light with your arm or your hand. Also, if your planet, you know, depending on the size of your light source, a little change in height of the planet could make a big difference. So when we're trying to control, if we want to compare size, we want to keep all of those other things constant. So we don't want to have a planet that's moving really fast versus really slowly, or moving at a different height relative to the fake star. We want to try to keep all those variables as constant as we can. And there's still going to be some variation, right? It's going to be hard to make your hand move at the same speed. And that's why doing a few test runs is pretty good. Okay, so you can see here, you've got 3 dips, all the same, roughly the same looking in those cases. Now we're going to try to do the small planet, or if you've been doing the small planet, try the large planet. And again, we'll try to go at the same speed. And what you're trying to look for is to see, okay, is there a difference between the small planet and the large planet? And if there is, what is the difference? So here's the screen that I'm getting for the small planet. So what I've noticed is that the dips are the same width. That's probably, so that's one thing that we can think about. Is there anything else that people are noticing about these planets? You can put them in the chat if you want.
So anything about the shape of your graph, either if it was like your predictions or if it was different from the predictions, or anything you noticed just from the shape of it while you were doing it?
What color line should we look at is a question. So make sure that you're right in the, are you using the physics toolbox? When you open physics toolbox, you might actually be in the wrong meter. You might be in G-force meter. If you push on the hamburger menu bar, so that's the 3 lines in the top left of the app, you're going to get a drop-down menu, and you're going to scroll down and you're going to select light meter. You'll know you're in light meter when it says light meter at the very top of the screen here of the app. If it says something else, you're using one of the other physics toolbox features. We're trying to use the light meter, so make sure you're using that. I think the G-force menu has 3 different color lines, but that's not what we're trying to measure. It should say luminescence. It should on the y-axis, and on the x-axis, it should be running time across the bottom of the screen. So I think that might be the problem if you're having different colored lines.
And it looks like Eloise might have a question too. Are you raising your hand for a question?
Yeah.
Yes, please go ahead then.
When I clicked on the light meter, it says light sensor not detected.
Oh, are you using an iPhone?
Yeah.
Yeah.
Then you needed to use Science Journal, the Science Journal app. The physics toolbox only works for Android.
Okay.
And I'm guessing you're probably not the only one who has that problem. So I think in the information Kelly had given us, it mentioned that, but it might have been in detail that's easy to overlook. And it's a bit of a complicated answer where Apple doesn't give third-party app developers the rights to access certain sensors. So an iPhone does have the sensor, but it's just the physics toolbox can't use that. So anyone else who's also using an iPhone, you would have encountered that exact same problem. So you need to use Google Science Journal or possibly another app, but that's the only one we know of that'll have a working light meter.
I actually have an app that is doing pretty well. It's showing the level of light, and when I go to the beginner light, it's like going up, and here we can like when I put it closer light, it's very high, and then
so that there are many light meter apps like that, and that's fantastic if you want to use that. The only thing with that one is you don't get the graph. So you won't see a plot of the light and then a dip in the brightness when the planet passes. You're going to have to figure that out looking at the numbers. Now that could be a fun experiment to try. If you wanted to write down the numbers, you could try to do your own graph by doing a record of the numbers, and that's totally fine too. So there's the two apps that we recommended actually show on the screen. I'll just do a quick screen again. They'll actually show you on the screen a little dip in the brightness. So you can actually see in a plot what that's going to look like.
Yeah.
But there's a lot of other light meter apps there that are used for photographers that are trying to get a measurement of the light, and they're just getting the number. They only care about the number. But you can use those to make your own graphs if you wanted to record the data as the planet is passing in front, and then you could make your own graph.
Okay.
And that would probably be a lot easier with the planet going really slow as well. If it's going fast, it might be harder to know, like for the shape of the graph, when it changed. It might be a bit difficult.
Yeah, but you can, if you have that app on now, you can certainly get a sense for the difference between big and small, you know, at the moment. Are there other questions or problems with the setup?
There was one question about distance versus brightness.
Yeah, I'm not sure I understand that question. What about distance versus brightness? So you could do that, but as I mentioned before, so you could do that, but this is going to be a bad model to show you those effects because our detector is so much closer to the light source than in a real system where our detector would be really far away. So if you play the distance of the planet, you'll notice a difference, but that's because the distance, this distance here is very, very small in comparison to the enormous distance of our telescopes to a distant star and the small distance that's between those. So you will notice a difference with this setup, but it's not a great model for what we would really be doing when we would look at an exoplanet because the distances here are so compressed. So it does make a difference, and that's an interesting test you could do with this setup. But it won't tell us a whole lot about how those exoplanet detections are made, because normally this detector would be really, really far away. And so any change in distance of the planet that's close to the star would not really be noticeable.
And it got me thinking about a couple of other limitations for light bulbs. Like if you were trying to do a setup like that, where you'd make the phone like all the way to the other side of the room to make it slightly better. Because a lot of modern light bulbs, they're not good point sources of light, so you're not going to have the inverse square law for the intensity of light as you move away if it's at all directional. So that part of the model wouldn't even work out well, no matter how far away you move the phone.
That's true. Yeah. Yeah. All right, well, let's try now maybe changing the speed for those of you who have the setup. One of the things that hopefully you've made some, we'll talk about the results maybe at the end for everything. Try to make some notes on what you're noticing, and then we can talk about it a little bit. So what I'll do is I'm going to choose the big planet, and I'm going to go by really, really slowly.
And just before we start getting results for that, Eloise seems to have another question. Eloise, can you go ahead?
Oh, sure.
The science journal, when I'm here, it says welcome to Science Journal. How exactly do I get on where it shows you how much light there is?
So hopefully there's a drop-down menu. I don't actually have an iPhone myself, so it's going to be hard for me to walk you through it. From people that have had an iPhone that told me about this app and they showed it to me, there should be a menu that in the same way that the other app had many different features that you could pick, there should be a light meter app or a light meter tool in a drop-down menu.
Thank you.
And if you still have trouble finding it, let me know, because I have Science Journal on my phone, but I'm just not as used to using it because I usually use Physics Toolbox for most things, or Firefox, which is another app. But if you continue having problems, I can, like while Kelly's doing the experiment, I can look for it on mine. So did you find it, Eloise?
Not exactly.
Okay, so we'll let Kelly continue with the experiment for the others, but in the background, rather than following on in the experiment, I'll be frantically trying to find it on my phone so I can talk you through that. Okay?
I know how to do it.
Oh, someone says they know how to do it?
You press the plus at the corner.
Yeah.
Oh yeah.
You go to this, the graph,
Yeah.
and you hit the little light bulb, and it should have a light graph.
Did that work?
I don't see the light bulb.
Under where you switched it to the graph mode, there should be a bunch of symbols.
Yeah.
Tap on the light bulb.
I see a music note, a circle with an X, a circle with a Y, and a circle with a Z. But I can't see the rest.
Scroll to the right, and you will see it. Do you see the bulb?
No.
Oh. Yeah. Once you are in the main menu with X, Y, and Z, if you scroll to the right, you should be able to see the bulb, the magnet, and so on. Let me show you.
Yeah, I'm on the same page.
Yeah. So once you are here, you have to scroll to the right. Okay? And here you will find the bulb.
I scroll. I can't do it.
Maybe because it seems like it might take a while to try and fix that. Maybe we'll continue, but if you continue having problems with it, maybe send me an email afterwards and we can try and sort things out for that. Does Does that make sense if we continue?
Yeah, that's okay.
Okay, so sorry about that, and thanks to everyone who jumped on to try and help resolve that problem.
Yeah, thanks very much. And there, you know, there's always new apps coming out, and so if other people find apps that work really well, feel free to share them. That's always a nice thing. There's always new things coming out. So we tried. Hopefully, you've been able to try the size of the planet. We're going to try speed now. So I'm going to take this big planet and I'm going to try to go very, very slowly. Have it transit my fake star. Now, ideally, I'd like to do it 3 times, but I'm going to do a fast one so I can have both screens on to show you. So you should see this dip here was the slow and that one is the fast. So we'll try that again. You can also take screenshots with the app too, and then also scroll back. So here's a slow one. And then I'll do a relatively quick one. And show you my screen there. So maybe what we'll do now is chat a little bit about some of the differences that we see between these 2 cases. I'm going to come back over here and we can talk about what you guys are noticing. Do you see a difference between moving fast or slow with those curves?
So anyone, feel free to jump in, either on your microphone or writing in the chat. What are some of the things you see as a difference between the graphs? Seems like a lot of people are pretty shy. Oh, looks like Deanne Rose has her hand up. Yeah, we'll call on you. What do you see?
On the large exoplanet, it's 5 seconds. So
Okay, so I feel like I see for the speed something that looks quite close to what I had, slow versus fast. For slow, you have a really wide curve because the planet is spending a longer time in front of the parent star. And for fast, it's a very narrow one because if you look at the time on the x-axis, it's spending just a short time in front of that planet because it's moving so quickly. Now, the large versus small, it could be that, you know, there could be something about the setup. I'm not arguing that those aren't your observations, but what I noticed in mine for the size of the planet was that it was, as Vernita also mentioned in the chat, that it was how deep that curve is, which I see a little bit in yours. The large exoplanet is deeper, but you also have it wider, and that's more of a time thing. But certainly that looks really great. And Vernita has also mentioned now in the chat, when moving fast, the curve is smaller. Anybody else have anything they want to add or things that they saw are different?
And just for that description, smaller, often we want to try and be more precise. Do we mean smaller in terms of less wide, which would be narrower, or smaller in terms of less deep? Because those can mean 2 different things. Sometimes they go hand in hand, but not always.
Yeah, so I'm seeing Vernita has added narrower.
Excellent. I think that's what we noticed as well. And on my phone, they seem to be just about as deep as each other.
Okay. So I'm just going to share my screen again here and show you hopefully what you might see. And if you haven't seen it yet, you can just try it out a few more times at home. But we're going to just carry on now, I think. These are the observations that you may have seen. So for a large exoplanet, you get quite a deep curve. It blocks a lot of light. Versus a small exoplanet, if we keep the speed the same between the two trials, it's really just a shallower curve. The speed of the planet, though, affects the width of that curve. So a slow-moving planet will block the light for a longer time, and a fast-moving planet will block the light for a shorter time, but the amount of light that it's blocking stays the same. So that's what you might notice. Again, depending on how you're holding it, if your arm gets in the way or hand gets in the way, you may introduce a change to your curve. So that's why it's really important to do it quite a few times so that you can be sure you're eliminating any of those possible sources of mistakes. Okay. So I thought we could also talk a little bit about the real data. Hopefully this gives you a sense of how the method works and how it's done. In reality, the challenge is really, really big when we do this because the amount of light being blocked is extremely little. So this is a graph showing real data. And if you look at the y-axis, one here is 100%. But if you look at the amount of light that's being blocked, it's less than 1% is being blocked. And this is for a solidly confirmed planet. So the when it comes to doing this, it's actually quite challenging. The amount of light that's being blocked is very, very small. This is really blown up here, right? 1, and we've got at the bottom of the y-axis 0.992. So it's only a very small amount. And then you'll notice to actually confirm a planet, we need to see this happen at least 3 times. That means the planet needs to go around the parent star 3 times. So if you're very close to the parent star, and the distance you need to travel is only little, you might go around every couple of days, which is the case for this planet, right? It's doing an orbit every few days. But think about a planet in our solar system like Neptune. You would need to wait years to be able to confirm a planet like Neptune. So our methods tend to confirm planets that are big and close to the parent star. One, because they block a lot of light and they're going to move quickly so that we can confirm them in just a short amount of time. Now, the biggest and probably the most important exoplanet observatory was the Kepler mission that was completed in 2018. It observed thousands of planets, and it was only looking at a small patch of sky in the constellation of Cygnus the Swan. And so this is when planet hunting really exploded. Since then, TESS has been launched. So this is the new Transit Exoplanet Survey satellite, and there are others too. The European Space Agency also has its own planet hunter. This is the one launched by NASA. And they are also, this mission, TESS, is expected to detect 20,000 exoplanets. So there will be many, many more exoplanets that are going to be detected. One of the coolest ones that was detected a few years ago was this system called TRAPPIST-1. This is a system around a cool star. So even though these planets are very close to the parent star, because the star is so cool, these planets are actually, 3 of them are in what's called the habitable zone. What does that mean? It means that liquid water can stay on the surface of the planet, could stay on the surface. It doesn't mean that it is on the surface. Because if you think about the methods that are easy when we detect these planets, if they're very close to the parent star, meaning we see them orbit 3 times very easily, they're probably not planets that you would want to live on because it would be extremely hot. And so if your methods prefer finding planets that are close, you're going to want to look for cool stars so that they don't burn your planet up to smithereens, if you're interested in looking for life on other planets. Now, this TRAPPIST system has 7 rocky Earth-sized planets, but 3 of them, E, F, and G, were considered to be in the habitable zone. Now, that doesn't mean we'd want to live there. And to kind of, this is actually an animation showing the planets orbiting. You can see the different dips in the curve for each of these different planets here. But everybody is very excited. NASA actually has a whole website devoted to this, so it's a pretty cool system. You can go to TRAPPIST.1 and you can look at all the different data on these different planets. And I mentioned that 3 of them are in the habitable zone. Habitable zone is actually not a great word for it because these planets may not be habitable. And to give you a sense, right, both the Earth and the Moon are the same distance from the Sun, but we would not want to live on the Moon. So the Earth's moon is in the habitable zone too of our solar system, but it is not a habitable world, nor does it have liquid water. And the reason that it doesn't is because it doesn't have an atmosphere. And so while we can look at these different planets and we can figure out where they're located and we can see how big they are and different things like that, what is the big challenge to finding out whether a world is really habitable or not is being able to look at its atmosphere. So that's the next challenge that we have in exoplanets, is to see if we can measure atmospheres. And that has started. So the Hubble Space Telescope, shown here on the left, has started to make measurements of planet atmospheres. How does it do that? It takes the light that's traveling from the star, and some of that light just grazes through the planet's atmosphere. And when it does that, atoms that are in the atmosphere absorb some of that light at specific frequencies. And so you can actually see the fingerprints of different chemicals that are in the atmosphere by doing this. It's very difficult because only a small amount of light is going to graze through that atmosphere. So it's very hard, but we can make measurements about how puffy the atmosphere is and what its composition is when we do this. So Hubble has done that for a few planets, including some in the TRAPPIST system. But the real exoplanet atmosphere hunter is going to be the James Webb Space Telescope, shown on the right. That's supposed to launch in 2021. It was specifically designed with the idea in mind that it would be measuring exoplanet atmospheres. And so once that telescope is finally launched, we should finally be able to have this new piece of the puzzle in being able to say whether a planet is truly habitable or not. Because being in a habitable zone doesn't tell you very much. So that's some of the exciting stuff that's coming out with planets. There's many different projects that are looking for even more planets and planetary systems. But I think one of the exciting things in terms of searching for potential life or looking for planets that are much like Earth will be in our ability to measure their atmospheres. Any questions that people have, feel free to put them in the chat. If you have questions about exoplanets. If questions pop up, I also wanted to take a moment just to share some of the things that you might be interested in at Perimeter's site. If you're a teacher, and even if you're a student, we have resources for students from grades 5 all the way through grade 12. They're all free. You can download them. Many of them come with videos. So this activity that I did with you today comes from our Figuring Outer Space resource, and there's 6 activities in there. And there's a video, so even as students, if you wanted to download the resource, it's all free, you can download, and there's a video that comes with it. Some of the videos are on our YouTube site as well. I wanted to mention that we have, if you go to insidetheperimeter.ca, we have a page devoted to stay-at-home science, so you can look at all kinds of cool material on that page for students. And we have something called the Quantum to Cosmos Scale, which is a tour of the universe from the very smallest scales up to the largest scales of the observable universe. It's sort of like an interface like Google Maps. And on our website, we're going to be posting a scavenger hunt for that. There's also interactives that let you play with the Event Horizon telescope, the telescope that took the picture of the black hole, and learn about LIGO and gravitational waves. And then the last thing I wanted to mention is that all of our public lectures are online, and we're doing an online public lecture next week on May 6th at 7 p.m. Eastern Time. It may not be a great time for those of you who are in Europe. That might be too late at night, but they're all posted online the next day, so you can watch them. This one is going to be a conversation with astrophysicist Katie Mack. She's going to talk about the expanding universe and dark energy and dark matter and all kinds of cool stuff. And all of our public lectures are posted, so you can check those out online. But this one, it will be up by the next day if you're not able to watch it live that evening. I haven't noticed any questions yet. Michael, have you noticed anything yet?
Yeah, there was one in the chat asking about using an amateur telescope to observe a transit. Is it possible to do that?
No. So even all of the telescopes that are doing this would be doing this, most of them anyway, are doing this from space. And the thing is that with an amateur telescope, even if you have a camera, this transit is going to take quite a long time. So, and you need to watch that star for a very, very long time and have your camera on it all that time. So day and night, as the sun rises and sets, is going to really mess everything up for your ability to detect an exoplanet. Now, there are cool things that you can try to detect with an amateur telescope, and one of those would be asteroids. And people do look for asteroids with amateur telescopes. You can even measure the asteroid rotation, because depending on the shape of the asteroid, the sunlight that it reflects, it'll be potato shape versus round shape. And so you can calculate you can measure the amount of light that you're getting from that asteroid, and you can actually determine its shape and things like that. So amateur astronomers do that. But it isn't really possible to detect exoplanets with anything that you would have available to you at home, even the largest telescopes.
I thought of a question while listening to your answer to that. You were saying doing anything on Earth, then any of your measurements would be affected by day and night. And I've never really thought about space telescopes, but are they orbiting at a level where like day and night become irrelevant, or is that a problem that they need to, like the Earth either shading them or being in full sunlight? Is that a problem, or no, because it's facing away from the sun anyways?
So it can be a problem. So the James Webb Space Telescope that I mentioned is designed to measure at long wavelengths, so infrared, mid-infrared wavelengths. And so any bit of light from the sun is going to overwhelm that telescope. So it is designed with a huge heat shield to completely block the sun for this reason. So they're also often powered by the sun. So the backside of the heat shield then has the solar panel that it uses to collect energy as well. There's other methods that they use to power them too, but the solar energy is part of that. But telescopes, depending on the kind of telescope, especially if, you know, something like Hubble can direct itself away, it is directed away from the sun. But especially something that's doing measurements at longer wavelengths, it's going to really need to protect itself from the sun and have a large heat shield. If I even just go back to that slide of the James Webb, you'll notice there's this like accordion thing at the bottom that sort of looks like it's the sail, it's the base of a ship. There's this layered thing at the bottom. That's the huge heat shield. So that is basically layers of material that are protecting the telescope from the sun.
That's really cool. Are there other questions anyone else has? And it's looking like we probably don't have any other questions. if things do come up afterwards, feel free to email me, and probably I can pass questions on to Kelly if it's anything you guys are wondering following this. But now I'd like to thank Kelly again for joining us for this session. It was really amazing to have you along and to have you share all this with us on Exoplanets. So again, thank you very much, Kelly.
Yeah, thank you for the opportunity and for taking time out of your day to join me.
Thank you.
And really, everyone, do check out Perimeter's resources because they do have a bunch of great stuff on there as well. And thank you, everyone, for joining us. Thanks for sharing in this adventure. And remember to stay home, stay safe, and above all, stay curious.